In this last lecture on LEDs, I'll discuss the frequency response of LEDs, the optical light extraction, and some aspects of device fabrication and reliability. I've already discussed the properties of the p-n junction, which gives rise to light emission when electrons recombine with holes, giving rise to light. Now the question is, how do we get this light out from the device? I've already discussed that there are two types of substrates, transparent substrates and opaque substrates. Opaque substrates are gallium arsenide based, which absorb radiation because h nu is greater than Eg, whereas transparent substrates are things like gallium phosphide, which can reflect the light back to the top. Now, if we consider light originating in a semiconductor, and there is a semiconductor air interface or semiconductor dielectric interface, then if the refractive index here is N1 and refractive index in the semiconductor is N2, then we know that by Snell's law that when light emerges, it is bent N1 sine theta 1 is equal to N2 sine theta 2, and there is a critical angle theta c. The critical angle theta c is given by sine inverse N1 by N2. And since N2 is large, this theta c, the critical angle, is rather small. Beyond this critical angle, we know that light will be totally internally reflected. So this is a problem with semiconductors, because N2 is quite large, of the order of 3, and if we look at typical semiconductors like gallium arsenide or gallium phosphide, for gallium arsenide, if you look at N2 and theta c, gallium arsenide N2 is 3.66, and the critical angle is only 16 degrees. This is much larger for glass air interface, because remember, glass, the refractive index is only about 1.5. For gallium phosphide, refractive index is slightly lower, 3.45, and theta c is 17 degrees. Okay, so this means that if you read all, the critical angle is the angle made by the ray with the normal. So this critical angle is only 16 to 17 degrees. Okay. All the rest of the light will be reflected in. So there's only a small amount of light coming at the right angle. The cone obviously will be twice theta c, which can get out into air. Okay. This is a major problem which has to be overcome. Okay, so this is called the critical angle loss. Broadly, we are talking about what are the optical losses after conversion from electron-hole pairs, 2 photons. What are the problems of extracting light from the device? There will obviously be reflection losses. Even at normal incident, we know that quite a lot of the light is, the reflection coefficient at normal incidence is given by N2 minus N1 over N2 plus N1. And we've seen this from the point of view of photodetectors, that this can be quite large. It can be 30%. And this is generally overcome in the case of especially lasers and other high quality devices by having an anti-reflection coating. Okay. And the third loss is absorption within the material. After all, we have a N plus P or a P plus N junction. Okay. So these heavily doped layers, we can get some amount of free carrier absorption. And of course, if the emitted light is near the band gap, also there will be quite a lot of absorption. So for example, as I mentioned, that if you have gallium phosphide with zinc oxygen, okay, lambda emission is much larger than lambda critical. So you have no absorption, no material absorption. But on the other hand, if you have something like gallium phosphide with nitrogen, okay, then lambda emission could be something like the tail of this cutoff, and then you will have material absorption. Okay. So in order to get over these problems, some optical design is required, and there are two methods of overcoming this problem. One is having the light semiconductor made in the form of a semicircle, so that the light is emerging always quite close to normal, near the critical angle. So if you have a semiconductor fashioned in the form of a hemisphere, the light is will come there, it will go out. Light here will not be too far from the critical, and that also will come out here. Okay. Light would also come out. Okay, so one idea is having, these are the contacts. Okay, so you could make a contact here, one contact here. So you have a semiconductor with a hemispherical shape, which will give you greater light output. But fashioning a semiconductor in this hemispherical shape is going to be expensive, so these are rather costly devices. They're not easily available. They're very special purpose devices. On the other hand, what is often done is to have a dielectric or plastic dome. And I'll show you devices like these, okay, which are embedded in a plastic dome, and hence the light output is higher. The construction of this is as follows. If you have these little chips which are mounted the top contact is taken like that to a pillar, okay, and this is the bottom contact. You have the N plus P, say, device, and the whole thing is embedded in a it's typically a plastic which has a refractive index of the order of 1.6. Okay, so this is what is known as a dome, dielectric dome LED, and just with this configuration, the light output can increase by a factor of about 6. Obviously, these plastic domes are rather soft. They won't stand high temperature, but nevertheless, they're cheap enough to manufacture in large quantities, millions of quantities, and as a result, the price of these little LEDs is typically of the order of about a rupee each. I can show you packets of these LEDs, green, yellow, and red, which are commonly available. And if I ask you what is the constituent of these LEDs, you should be able to answer. What are the green LEDs made out of? Yeah, green will be gallium phosphide with nitrogen, okay, because the band gap has to be large enough. Yellow, will also be gallium phosphide with slightly lower amount of nitrogen, etc. Okay, and the red. Okay, now for the red LEDs, there's a choice. There's a choice of at least 3 types of red LEDs which can be made, and there will be subtle differences in the spectrum, okay, in the price, in the efficiencies, etc. And what you've said is on the right lines. Red LEDs can be of 3 types. One is gallium phosphide, zinc oxygen. If you remember, I said that historically the first type of LEDs was gallium arsenide phosphide, graded, okay, and I can draw that. Obviously with zinc doping, okay. What is the structure of this? I might as well discuss this while I'm. Traditionally, this was the first. Why? Because gallium arsenide substrates were available, gallium phosphide substrates were not available. So on a N plus gallium arsenide substrate, doped with, say, silicon, we grow a graded layer, N gallium arsenide phosphide, tellurium doped, N-type. Here, okay, the substrate thickness may be 350 microns. The graded layer thickness may be something like 15 to 25 microns. Here, this X is increasing, okay. This is to avoid lattice mismatch, okay. So the dislocations in this will be limited to near the interface. So X increases until then you have a constant composition layer. This is N gallium arsenide 0.6, phosphorus 0.4, okay, This is also 15 to 25 micron. Okay. This is the active layer. And in this, you, using silicon technology, using a mask, photolithography, etc., you diffuse a P plus layer, zinc doped. Zinc diffuses very fast, so it's done at relatively low temperature, very short time, and construction is completed by, obviously you have a silicon nitride mask here, insulator on which the ohmic contact is placed, metal contact, okay. This could be this P-type, so the ohmic contact would be aluminium, and here you have a gold wire. And on N plus gallium arsenide, what would be suitable ohmic contact? It would be typically something like gold tin, okay, or it could be gold germanium. Whereas here, instead of aluminium, it's a P-type material, so you want something like, you could have gold zinc also. But obviously gold zinc is more expensive than aluminium, so aluminium would be chosen. Okay, this is the structure of the good old gallium arsenide phosphide zinc doped red LEDs. What is the third possibility? Oh, incidentally, these layers can be, see, on the 350 micron substrate, you grow this first a graded layer and then a constant composition layer. These layers can be grown, LP is very good because you can grow fast. These are quite, it's not sub-micron, okay, it's the total thickness may be something 30 to 50 microns, okay, so you can't spend a whole day growing the layer. So LP is very good, or VPE is the and this is a lattice mismatched. So if you have dislocations, the dislocations, due to mismatch here, the dislocations hopefully will remain in this graded layer. This is graded. Composition, graded meaning composition varying with distance. Okay. At the beginning it's gallium arsenide, and here it's gallium arsenide phosphide. And X is changing. What is the third type of red LED that one can talk about? That is based on this gas-algas. Okay. And these are quite commonplace, and you can get rather higher efficiencies. Because why? Because these are double heterojunction LEDs. Okay. So I drew a diagram of these double heterojunction LEDs, and you will get light confinement, carrier confinement, and you'll get rather higher efficiencies. Okay. There will be subtle differences between these LEDs as far as the emission wavelength is concerned. Okay. Also, the IV characteristics, the efficiencies will also change. For example, double heterojunction LEDs will have higher efficiencies. Okay. Also, this is a direct gap material here. This is the others are indirect gap materials. Right. When I'm talking about this, I can discuss what is the spectral response typically. So this is not a red emitting LED. A typical infrared emitting AlGas LED could have lambda emission at about 835 nanometers, and delta lambda will be something of the order of 40 nanometers. So 400 angstrom. So the spectrum is quite wide. This is the intensity, function of lambda. Okay. 735, 935. Okay, this is the full width half maximum, which is, and you can see the 835 corresponds almost to the band gap of gallium arsenide, right? So this is a gas Al-gas LED in which the active layer is gallium arsenide. Okay, and the aluminum gallium arsenide forms the confining layers, right? Because this corresponds to 835 is about 1.4 EV. Okay, why is this line width broadened? There are this is, firstly, it is due to spontaneous emission. Okay, there is a spread of energies of the electrons and holes of a few kT. Okay, so apart from that, we have heavy doping effects, because for high injection efficiency we need N plus P or P plus N. So heavy doping is one contributor. There is thermal broadening due to distribution of energies of the carriers, and in case of ternary materials, say in the case of gallium arsenide phosphide, you have alloy broadening. Okay. Alloy scattering also contributes to broadening. So this is 400 angstroms is a fairly broad spectrum. It's fine for display devices, obviously, but if you want to use these devices for communication, then obviously this is too much, because the different wavelengths will travel with slightly different velocities, and you will get spectral broadening. These are just PN junction devices, so if you just look at want to characterize them through electrical measurements, you can have the IV characteristic of the device, which will be something like that. The forward cut-in voltage will be an indication of the band gap of the material. Okay, and in the reverse bias direction, you will get breakdown, and the VBDs are not very high because these are rather heavily doped, so about 5 to 15 volts. So this will also give you an indication of what is the composition of the material. And the most important characteristic is, of course, the light output. Intensity measured in, say, microwatts. Microwatts is a fairly large amount of power. 1,000 microwatts is a milliwatt. So typically these LEDs emit not milliwatts but microwatts of power. And if you plot IDC in milliamps, and say this is 100 milliamps, you have a linear Li. This is called the Li characteristic of a light emitting diode, and this is the most useful characteristic from the point of view of its applications. Later on we'll see that for a laser we have a highly nonlinear characteristic light output, because when it starts we have spontaneous emission, and then suddenly at the laser threshold the current will go up. Okay, so very sharply. So this is for a laser, and this is for LED. Now, we've said that the applications of these devices are for displays, where the color is more important. And of course, low power, we want high stability, high reliability, low degradation with time. Okay, for example, it's been seen that the talk about degradation. Suppose you want to test these devices. Okay. Suppose you have a certain power output versus time, and for AlGas devices, you start off at, say, a certain value of 100, and there's only a very small loss. So test for 8,000 hours. Typically, one tests for 8,000 or 10,000 hours. There's a degradation of only a few percent. Okay. So these are highly reliable devices.
So efficiency decreases.
Yeah, efficiency decreases. Obviously, the light output also decreases. One may ask, what are the main reasons? Obviously, there could be effects, thermal effects due to continuous heating. There could be little diffusion. There could be formation of defects, formation of point defects or line defects. These are the main reasons. I'll talk about that a little later. And so these are relatively, they're not high power devices. They're low power. They're from 100 microwatt to a few milliwatt. Usually, okay. But lasers operate with a few milliwatts to even up to a watt. So the degradation mechanism of lasers is slightly different, and they can degrade quite fast. Now, if we talk about applications in communications, fiber optic communication, or even direct free space communication, then one of the most important parameters is the frequency response. How fast can these devices be switched on and off? What is the frequency response of LEDs? Okay. We know that we have calculated that the spontaneous recombination time is of the order of about 0.6 nanoseconds. Okay, so this is connected with the minority carrier lifetime of a device. Suppose you are injecting carriers, okay, they live average of about 0.6 nanoseconds, say 1 nanosecond. Suppose the input signal is faster than this, then obviously the carriers cannot follow, they cannot keep up, and obviously the response will decrease because the carriers are not being able to recombine and give rise to light. So that is one factor, which I'll go back to and we'll do a little calculation. And as in the case of all...
Sorry, carrier lifetime is less than high frequency response high.
Yeah, right. If you can intentionally reduce this recombination lifetime, okay, then frequency response will be higher. Remember, this, say, 1 nanosecond corresponds to 1 gigahertz. Okay, so that's quite high. Okay, so typically, almost something like this can be achieved. But there will be obviously a trade-off between power and frequency response. Okay. The other response time is due to RC time constant. Okay, it's a device. So what is capacitance? capacitance is C is equal to A epsilon 0 epsilon R by D. Okay. So if you want to reduce, so you reduce the area. Okay. So if you have a much smaller device, these C will be lower and the RC, and of course you can also reduce the series resistance. That will also reduce the power dissipation. Okay. One possibility is reduced area. The other possibility is, suppose you you increase the reverse bias when you switch off. Okay, increase the reverse. 1 by C squared against V. So if you increase the reverse bias, the depletion width increases and the capacitance decreases. Let's look at the effects of the first factor, the effects of charge storage and diffusion capacitance. These devices are operated at forward bias, right? When the minority carriers are injected. At forward bias, you have injection of minority carriers, which gives rise to diffusion capacitance. And obviously that limits the speed of response. Now, if we want to examine this, it's typical for almost any semiconductor device. Let's examine this in a little more detail. Suppose we have a gas-al-gas structure, double heterojunction LED, and gallium arsenide is undoped active region, and this is al-gas P. This is the active layer width, and under forward bias we are injecting minority carriers into this region, okay. Electrons. We want to look at the time response of this, so we examine the continuity equation. The electron concentration as a function here of time. The electron concentration here changes with time due to two reasons. One is recombination, spontaneous recombination rate, and due to diffusion, d2n dx squared. Okay. So there are two terms. This is the recombination term, and this is the carriers are injected and they diffuse out. So we know that RSP, spontaneous rate, is just nothing but nx by the lifetime. So we can write the expression delta n delta x delta t is equal to minus nx by tau plus dE. Now, most of these LEDs are operated, there is a DC forward bias plus a signal frequency, which is modulated, okay, at say a frequency omega. Okay. So the carrier concentration nxt has a steady component n0x plus a time varying component n1x e to the power j omega t. Okay. Now, if you substitute this into this, you will find you get two equations. One is the DC part. The DC part is dE delta 2n 0 delta x squared minus n0 by tau is equal to 0. And the AC frequency dependent part is obviously this n1 comes in, delta 2 n1 over delta x squared minus n1 now to get the solutions of these equations, we know that LE is the diffusion length. Under DC conditions, it's dE tau to the power half. And under AC conditions, we can say that LEW is equal to, let's define this as dE tau over 1 plus j omega tau to the power half by analogy. Then the AC equation becomes d2n1 over dx squared minus n1x over LE squared omega is equal to 0. What are the boundary conditions? Boundary conditions are that n1x is n1 0. That is at x equal to 0. If you look at here, and we say that this D is much larger than the diffusion length LE. Okay, so D being much larger than the diffusion length, N1 D is equal to 0. Okay, so the carriers are injected and they decay much before they reach the boundary. So we can say that N1x, this is obvious, they are decaying, so this is just given by N1 0 e to the power minus x. This profile is exponential minus x by LEW. So what are we trying to calculate? We're trying to calculate what is the frequency response which is light output. This is the AC photon flux over the AC component of current density. Okay. So the number of electron hole pairs giving rise to the number of photons. Okay, so this is the AC. So phi 1 omega is nothing but 1 by tau, the average, 0 to d n1x dx. n1x we've calculated, so this is just n10 LE omega by tau. So we want to calculate J1 omega is equal to current is diffusion current, so Q dE delta N1x delta x, the gradient, and this is equal to minus Q dE N10 by LE omega. So we take the ratios of these two and we find that the response function is LE omega squared by tau dE, which is nothing but 1 plus omega squared tau squared to the power half. Where tau, we can say that if it is direct spontaneous recombination, as tau 0 is of the order of about 0.6 nanoseconds. So this is intuitively you can you can get this, but this is a full derivation. So the response decreases with increasing W according to this relation, and you can, if you draw the frequency response, say you have 1 at low frequencies, then you can what is the modulation bandwidth? You can, from the light optical point of view, you can define the bandwidth as where this drops to half its value. Okay, so this is the optical bandwidth. So the optical bandwidth is delta F dB is 10 log P out by at a definite frequency over P out dC. Okay, this is a frequency dependent, and this is equal to 10 log 10. If you I out, you measure the frequency output at a high frequency and at DC, and you compare the two. So the 3 dB point here is I output F by output DC is just half, which is what I've drawn. But you can also define an electrical bandwidth concerned with the power, which is proportional to I output F over I output DC squared is equal to half. And so in this case, I output F over I output DC is 1 by root 2. Okay, so that would be somewhere here. Okay, so the electrical bandwidth is the 1 by root 2 point, 0.707, whereas the optical bandwidth, as defined, could be 1 by 2 point. So you see that obviously this depends upon tau. Okay, the smaller the value of tau, the better the frequency response. So you want, as it was asked, how can you control this? Tau can be decreased by various means. One is by heavy doping, reduces the minority carrier lifetime, or you can have very high level of injection. So this amounts to increasing the current density and decreasing that width of the active layer. This has been worked out, and for example, you can show that this tau R is QD in the case of high injection by JBR to the power half, where tau R is 1 by BR delta N for this bimolecular mechanism. recombination mechanism. So you see that this can be reduced to R by reducing D or by increasing J.
Sir, for high level injection we have to increase tolerance.
Yeah, increasing the current density. Yeah. So overall, to sum up, there's a trade-off, obviously, between the LED speed and power. Get it? Overall diagram. This is power going from 0.1 to 10 to the power 2 milliwatts, and the modulation bandwidth going from, say, 10 to 10 to the power 4 gigahertz. Megahertz. Okay, megahertz. This is quite easily go up to 10 to the power 3 is here. That's a gigahertz. 10 to the power 1, 10 to the power 2. And for different types of devices, it's 0.1, 1, 10, you have a trade-off which is of this type. Get a just 10 to the power 1, 10 to the power 2. Somewhere. Okay, so for example, these are for the most highly developed gallium, aluminum arsenide, gallium arsenide LEDs, and these are for the indium gallium arsenide phosphide LEDs. Okay. So if tau is small, then you get very fast response, but the power output is low.
Why power decrease due to high speed? And if we operate at high injection level, current will be high, power high.
But
Speed also high.
the speed will be high, yeah. For that family of devices, the speed will be high. But you know the relation that delta N is, okay, G into tau N, right? So if tau N is very small, okay, the excess carrier density is going to be small, okay? So obviously then the light output will be less, okay? So there's going to be trade-off here. And to just give you an idea of what are the different types of reliability, I'll conclude just talking about the reliability of these devices. V-groove edge emitter LEDs. They work current density of 10 kiloamps per centimeter squared, maximum, okay? And they have lifetime more than 10 to the power 6 hours, extrapolated lifetime at 70 degrees centigrade. Okay? That's one type. Oxide isolated edge emitting devices. They work at about 2.5 kiloamps per centimeter squared. Again, greater than 10 to the power 6. For display devices, surface emitting, so surface emitters, high speed surface emitting devices, they work at about 32 kiloamps per centimeter squared, maximum, and greater than 10 to the power 7 hours. And you can also get another type of surface emitter that goes up to about 40 kiloamps per centimeter squared. And they have a lifetime greater than 10 to the power 6 hours. So this lifetime, extrapolated lifetime, 10 to the power 6 hours at 70 degrees, that corresponds to something like room temperature lifetime of 100 years. Okay, that's how reliable these LEDs are.